Hi everyone, my name is Liu Huiqi. Today I will present a topic in mathematical analysis, focusing on the concept of closed set in Rn. Closed sets are an important concept in analysis because they are closely related to limit, convergence, and continuity. In this presentation, I will explain the definition of closed set, and equivalent characterization using open set, some standard example, and finally, I will prove that a specific set in R squared is closed. Okay, let me first introduce the definition. This definition talk about let S in Rn, and we say that S is closed if the following condition holds. Whenever a sequence AK in S converges to a point A in Rn, then the limit point A must also belongs to S. In mathematically, we say that if AK in S and AK is converges to A, then A in S. And then I will explain the meaning of this definition in a more mathematical way. In mathematical analysis, sequences are one of the most important tools to describe convergence. Instead of directly studying geometric objects in Rn, we often use sequence because they give a precise way to describe limiting behavior. In fact, many concepts in analysis can be reformulated using sequence, which make them very powerful and important. So this definition means that if we take any sequence inside the set and it converges in Rn, then its limit must still remain inside the set. This means the set is stable under limit of sequence. Another important point is that in Rn, sequences fully capture the notion of convergence. This is why sequential definitions are widely used in analysis. Instead of dealing with complicated geometric structure, we reduce the problem to studying sequence, which is more manageable. Okay, there is also a characterization of closed set. A set S in Rn is closed if and only if its complement S is open. This result is important because it gives us two ways to study closed set. We can either use the sequential definition or show the complement is open. This equivalence is useful in proof because openness is a local property. This means that to prove a set is open, we only need to check what happens around each point using small neighborhoods. This is often easier than analyzing all sequences in the set. This also leads to an important geometric idea. Closed sets are closely related to boundary behavior. Intuitively, a set is closed if it contains all of its boundary points. Although we are not using this as a formal definition, it also helps us understand the meaning of closeness in a geometric way. Okay, then we move to the next part. Let us look at some standard example of closed set. First, the whole space R is closed. This is because every convergent sequence in R has its limit still in R. And the second one is the empty set is closed. This is also true because there are no elements in the empty set. So the condition is automatically satisfied. This is called a Wecker's true. And the last one is every finite subset of R is closed. This is because in a finite set, every point is isolated. So any sequence in the set must eventually become constant if it converges, meaning its limit must be one of the point in the set. Okay, and this example shows that how the definition work in both simple and extreme cases. Okay, and then we will prove. I will prove a specific example. First, let A equal to the sequence xy, where x and y is larger and equal to 0 in R squared. This represents the first quadrant in the plane, including the coordinate axis. We want to prove that this set A is closed. To prove this, we'll use the definition of closed set. Okay. Before we proceed with the proof, we first emphasize that we will use the definition of closed set because it directly connects the structure of the closed set with convergent behavior of in R square. Okay, and then we will prove it. First, let xn and yn be a sequence in A. This means that for every n, we have xn is larger and equal to 0 and yn is larger and equal to 0. And then we assume that this sequence converges to a point xy in R square. So we have xn is converges to x and yn is converges to y. And then we use a key property of limit. Is about if every term of a sequence is non-negative, then its limit is also non-negative. This is because limit preserve order under convergence when the inequality holds for every term in the sequence. Okay, this follows from the epsilon delta definition of limit, which ensure that the sequence eventually stay arbitrarily close to the limit. So, since xn is larger and equal to 0 for all n, we can conclude that x is also larger and equal to 0. Similarly, since yn is larger and equal to 0, and we can say that y is also larger and equal to 0, then the limit point xy satisfies that x is larger and equal to 0 and y is larger and equal to 0. So, xy is in A. This shows that every convergent sequence in A has its limit still in A. Therefore, we prove that A is a closed set. That's all for the closed set proving. And then we move to the conclusion part. In this presentation, we study the concept of closed set in mathematical analysis, and we introduce the sequential definition of closed set, which describe how the set behave under limits of sequence. And we also discuss an equivalent characterization where a set is closed if and only if its complement is open. And also we show the standard example, including R, the empty set, and the finite set. And the last part, we prove that a set is closed using the definition of closed set. Another way to understand closed set is through the idea of closure. A closed set contains all points that can be approached by sequence inside the set. This makes closed set very important in many areas of analysis, such as compactness and the study of continuous function. So, closed set form one of the fundamental building blocks in mathematical analysis. That's all for me. Thank you for your listening.